Hey, it's Tony from Adafruit, and in this video I wanted to look at MicroPython and how to talk to I2C devices. And I2C is just another way for two devices to communicate with each other, usually on a board or like with a small connection between them. So typically like a sensor or maybe a little OLED display has an I2C interface, which you can connect to a board like an Arduino, a Raspberry Pi, or a MicroPython board. And we'll see in this video stream how to use I2C operations like reads and writes to registers and memory to interact with the device. So in this case, I'm going to look at the MCP9808 high precision temperature sensor. Really nice little temperature sensor. It just tells you what the temperature is in Celsius and has a very simple I2C interface. So it's a good example of just looking at how you could talk to an I2C sensor with MicroPython. So we'll just kind of dive in here and get started. I'll jump to the main view. Let's see, we'll turn on desktop and everything else. So you can see here's desktop view, and in the upper right hand corner, so what I have here is the Feather Huzzah ESP8266 running the latest MicroPython firmware for it. So just a very typical board. Check out, if you're not familiar with MicroPython, in the description below when this goes up on YouTube, I'll have a link to the What is MicroPython guide that I did. So start there if you're new to MicroPython. You can learn about like what are all the different boards that run MicroPython, how to get started, how to load the firmware, that type of stuff. But basically you'll need a board that runs MicroPython, obviously. And then right here is the MCP9808 temperature sensor. And again, real simple, nice little low-cost temperature sensor. Great example of talking to an I2C device with it. And then on the desktop here, so I've just got a guide that was just published that goes into detail about how to talk to I2C devices with MicroPython. So I'm just going to kind of walk through this real quickly. I'm not going to spend too much time explaining what I2C is. You can check out the Wikipedia page. It's a little complex, you skim it a little bit, but it's not going to really give you the main idea. But again, I2C, it's very similar to like SPI or serial connections, two devices talking to each other with a few different wires. The I2C is an interesting kind of protocol or bus because it only really uses two wires. There's a clock line and a data line, and of course you have to have a power and a ground line, so there's really like usually four wires connected to a device. But just with those two wires, multiple devices can talk to each other. So in the last video I talked about SPI devices, the serial peripheral interface, and how with that you basically have one device that controls the bus and like specifically controls the clock line that all the other devices connected to it use to synchronize the communication so they can read and write data. Whereas with I2C, it's a little more interesting in that there's a clock line, but no single device controls that clock line. Actually, any device can take control of it. There's no device that's designated like the master that has exclusive rights to it. So some device can just pick up the bus, and they have a way to tell if it's in use or not. That's actually their pull-up resistors on the bus so that it normally stays at a high level, and then if someone pulls it low, then they kind of know if it's in use or not. But you don't need to really understand all those details. The basic idea is that multiple devices can be connected to this communication bus, and any device can talk to any other device. So they're assigned an address, and even inside of a device you might have like memory addresses that you're talking to, and we'll look at some of these basic operations. So again, it's just a really common way for devices to talk to each other. Sensors in particular usually have an I2C interface, but you'll also see things like little OLED displays might have that. I think like the motor and the PWM drivers that we have use I2C. So really, really common interface, and there are just some basic operations to learn with it, and once you get those down, it's pretty straightforward, and really all the complexity is just going to come around to what device you're talking to, what data it has, what format that data is in, that kind of stuff. And so we'll kind of dig into a data sheet here and see, maybe give you some pointers on how to figure that stuff out yourself. The other thing I should mention, if you're curious, check out this video, and I'll put a link to this in the description below when this goes up on YouTube. Maybe 9 months ago, almost? No, maybe 8 months ago or so. It's been a while. I did this video on more in the context of with the Raspberry Pi, what I2C is. In this video, it was kind of cool though. I used a logic analyzer. You can actually see right here, the Salier logic analyzer, and I looked at on the wires like what that actual I2C communication looks like. So you might check out this video if you're kind of curious how it works. And I look a little bit different since then. So that's me there. Trust me, that's the same person. Okay, we'll come back to this. This is the data sheet. We'll get started with the guide here. So basically in this guide, I talk about two different things. I make a mention of like an I2C master mode versus slave mode. this is really common in embedded stuff. You know, there's sometimes like a master device that controls the communication between a bunch of other slave devices. Like I said with I2C though, really any device can kind of be the master that talks to other devices on this bus. Any device can kind of take control of that clock and data line. So there really isn't as much of a distinction here. But MicroPython does make a little bit of a distinction because you could put some boards, not all of them, into a mode where they can act as an I2C slave, where they advertise themselves as a device, not necessarily advertise, but they listen for requests against a certain address. So you'll see with I2C devices, each one is assigned a unique address. And with some MicroPython boards, you can actually put it into a mode where you say, okay, I should act like a device that has this address and listen for requests and send responses back. So that would be good for if you're building like a sensor that's powered by MicroPython, for example, then you'd want to expose it potentially as an I2C device or peripheral or slave mode device like that. But it's usually not as common because typically you have a board, like a MicroPython board or an Arduino or something, that's running some code and talking to sensors. And in that case, you really just care about acting as a client or a master of the I2C bus. So that's what I'm going to focus on in this video, is just looking at how to talk to other I2C devices, not so much how to advertise yourself as an I2C device. And then the other big thing too, like a lot of things with MicroPython, you know, it's still pretty early in development, so things are changing a little bit, but it's still pretty cool and stable and worth checking out. But for I2C in particular, look at the documentation for your board because there are some small differences between the boards, some big differences too with some of the boards, but over time they're all starting to become very similar. But so I call out, in this guide, I look mostly at the ESP8266, but I do call out where there are differences. The Pi board has a few differences. Right now it's using this older interface from this PYB module. Eventually that's going to change to use this machine module that everything else uses. So just be aware, check out the Pi board documentation, and the function names are a little bit different with the Pi board. YPi is pretty similar to ESP8266. There's just one difference where you have to tell it to be an I2C master instead of a slave device. And then the microbit is actually really different than everything else. It has a very simple API. Basically, you can just read and write I2C data. I'm not sure that their API is good enough to talk to most devices. So, you know, just a word of warning that microbit, if you're expecting to do some crazy I2C thing with it, look at the documentation first and make sure it's going to work for it. It looks like it can really just read and write just bits of data on the bus. I'm not sure it can interact with devices, but that's at least the current state of the world. I'm sure it's going to change over time. So again, check out your board documentation to just see how things work. And then for this guide, like I said, I have wired up the MCP9808 temperature sensor. Really easy to connect I2C devices to boards. With the ESP8266, you do have some flexibility in that the I2C protocol is implemented in software, so you can use any GPIO pins. Now there are some downsides, like it's not going to be as fast, but for things like sensors, you typically don't need like super high refresh rates. Most fast devices use like a SPI interface where you can use the clock at whatever speed you want, usually like multiple megahertz. Whereas with I2C, there's a fixed clock rate. It's like 400 kilohertz usually, and I think there's like a 1 megahertz high speed mode. So usually it's a little bit slower with I2C, so you don't have like massive LCDs with huge amounts of pixels to push very quickly. But anyways, so with ESP, you have a lot of flexibility. You just have to connect up, your voltage, input voltage to power the device, ground, obviously. You need those basic connections. And then there's the SCL, the clock line. So that connects usually to GPIO number 5 on the ESP8266. And if you're using the Feather Huzzah, it's got nice little labels here. So just connect SCL to SCL. And then the SDA, the data line, that's connected to GPIO number 4. And so again, you've got a nice little labeled port there. But you could use any of the other GPIOs. Just be aware though, on the ESP8266, some of the GPIO lines have like pull up and pull down resistors connected to them. Like I think GPIO 15 has a pull down resistor, I want to say, connected to it. So you might run into weird behavior if you try and use some of these pins. Stick with 5 and 4. Those ones are known to work pretty well for it. So that's the basics wired up, and you're pretty much good to go at that point. So let's just dive in and start playing with some of the code for this. So I'm going to connect to the serial REPL for my board, and this is just MicroPython's REPL. And the first thing I'll do is I'll import the machine module So this is the module that has the hardware access API. You see this all the time. You know, if you want to access GPIO, SPI, I2C, everything with hardware, you're using this module. And again, on the Pi board, it's called PYB, but check the documentation. That's going to change eventually. And then the next thing is you create an instance of this I2C class. And for the ESP8266, you have to pass in the pin number for the clock line, not the pin number, but an actual pin instance for the clock line and the data line in that order. So in this case, I'm going to create an I2C device. We'll create an instance of the I2C class, and we'll pass it pin number 5 as the clock line and pin number 4 as the data line. So that's pretty simple and straightforward. For other boards like the Pi board and the YPi, they use a hardware I2C interface, where instead of passing in the GPIO pins, you pass in the number of the interface to use. So look at your board documentation. Usually you'll use like interface 0 or 1, just because most boards have like only 1 or 2 I2C interfaces. And one thing to note too is that for those boards, when you do use a hardware I2C interface, you usually have to use a specific set of pins. Like there's a very specific clock line and data line for that hardware I2C interface. So when in doubt, check the board documentation. The quick reference for all of the boards usually has a pinout description that just shows here are all the pins, and you know, you should look for like what is the I2C clock and data line, and that should help you find out which ones to connect to. So okay, so at that point then, you're pretty much set. Now there's a really cool thing with I2C. Like I mentioned, every device on the I2C bus has an address assigned to it, and it's just a 7-bit value, so 0 to 127. And I think the first few values are reserved, but you know, mostly about 100 devices can be connected to the bus. Now that is a limitation. Like you cannot have more than that 127 uniquely addressed devices on the bus. Like it's just not physically possible. If 2 devices have the same address, you're going to get a lot of confusion. Each one's going to try and respond to the same thing, and bad things will happen. So in those cases, maybe I2C isn't a good protocol for you, or maybe you need multiple buses to have more devices. Or I think there are I2C multiplexers, which are pretty complex things, but that could be an option too to look at. But the neat thing is, you can actually scan for what devices are on the I2C bus. So with MicroPython, it's beautiful. They have this nice little scan function that you just call, and this returns an array, a list of devices that it found and the address of those devices. And this is in binary, or in decimal, like just base 10. So this is a value 24. Now you'll want to usually go to your data sheet, and this is the MCP9808 data sheet that I have right here. For your device, because you're going to have to look up what is the address that the device exposes itself as. And so I'll go through this data sheet and we'll see if we can find it in here. So you can see, yeah, like right here, there's a concept of these address pins, and it's actually exposed on the breakout. There's these A0, A1, A2, I think, pins out here. And so if you pull these, I think if you pull them down or set them high, check the tutorial on this, it'll say specifically, you can actually set the address of this device, but you can't completely change the address. So you can see right here, some of these high order bits are always set, and then you can control the lower 3 bits here. And so I think by default they're 0. So just think of this as the binary value 11000. So if I go to calculator here and we just set this as 11000, and then base 10, you can see you get a value 24. So that's good. That basically tells us that we see a device on this I2C bus that has an address of 24 in decimal, or in base 10. So we see exactly the device we expect. We see the MCP9808. If I had multiple devices connected to this, and each device just shares the exact same clock and data line, like you can daisy chain all these connections, you can put them all in parallel. It really doesn't matter how you do it, but as long as they're all connected to the same clock and data line, and they have unique addresses, you should get back a list of each of those devices there. So it's a good little sanity check to be able to test, like, is the device there that I expect to see? And again, you don't really get this with other protocols like SPI, because they don't have a concept of each device having an address. That's like a higher level thing to add on top of the SPI protocol. So that's kind of a neat thing that you get with this. And then let's see, the next thing to do is to interact with the device. So this is where you get into some of the basic I2C operations, and you really do need to dig into your datasheet at this point to figure out, like, how do you talk to this device? So for the MCP9808, and usually in the datasheet there's like a section here on the serial communication, and this kind of goes into, oh boy, I just went to a different page here on accident. This kind of goes through what it looks like at like the physical level. So there's usually a diagram, you know, like this, that's showing you, okay, here's how the bits on the wire look, and here's how the clock line changes, and here's how the data line changes. But the nice thing is you usually don't have to worry about that, because a lot of the I2C details are taken care of for you by the software. So like the MicroPython code, it knows when it's talking to a device how to send the address, and there's a certain ACK bit and a NACK bit, and like, you know, an acknowledgement that things have been received. That's all taken care of for you. So don't really focus on that so much. The thing you want to look at for I2C devices in particular, look to see if the device exposes data using registers or memory. This is a really common thing where a device usually has an address assigned to it, so that you have to use that address when you talk to it. And then within the device, there's also an address of a register or memory that you want to interact with. So there's usually 2 bits of data that you need to know when you talk to a device: the address of the device and the address of the register or memory that you're talking to. And so this datasheet goes through all of the registers on this device. And it actually talks about, so like right here, these are the registers. So there's like this reserved one, there's a config register, temperature alert, upper bound, lower bound, critical alert. There's a temperature register. This is actually the one that we care about right here, that has the temperature value from the device, and then all kinds of other stuff here. So this is kind of handy. And then the rest of the data sheet usually goes through each register, like register by register, to say, okay, you know, here is the sensor config register, and here is, you know, this is 16 bits, you can see, and here's exactly what each bit inside of here means. And so you can go through, and it even tells you like, okay, you know, this alert control, this thing is readable and writable, whereas this alert status is only readable, you know, this R here. So, you know, different things might behave differently, and you really need to look at the data sheet to see how it works. Now let's go down to that temperature register on the data sheet here. So it's a little bit further down. It's register number 5, if I remember correctly. Yeah, the ambient temperature register. And you can see here, so they're showing the address here is the value 101 in binary. So that's 5 in base 10. So that's what we want to read. If I read this register, and you can see it's 16 bits long, there's some data inside of here. So there's actually these upper bits that tell you if you've exceeded like your lower boundary, your upper boundary, your critical threshold. Kind of an easy way to check, like you could set this upper boundary or lower boundary and then just look for that bit to tell if you've gone above some high level. You know, maybe you're building like a barbecue temperature monitor or something, and you know, you can set your upper boundary temperature to like 200 something degrees, and if it goes above that, just look for your bit to know that something went wrong, or that, you know, you're burning your ribs. But then you can see the lower 14 bits, or no, sorry, lower 13 bits here are the actual temperature data. So there's a sign bit, and this is all pretty typical stuff in that this is a 2's complement signed integer value. The annoying thing is that, you know, this isn't like a 16-bit or a 32-bit value that Python kind of can natively understand and unpack. So we've got to do a little more work to interpret this value, but I'll show you. I actually have a library for this already. It's really simple and straightforward. One of these days, though, I'm going to sit down and write a library that's an arbitrary bit length 2's complement value converter. You know, just throw in a 16-bit register, say here's where the value starts, and it's a 12-bit signed value or a 14-bit unsigned value, because I end up doing this like almost every time I deal with a sensor, and I'm reinventing the wheel a lot. But anyways, this is what I want to do. So I want to read this register, register 5 on device with address 24. So the way to do that is with a simple function from MicroPython. There's the read from _mem function. And so I show first, it's kind of helpful. Let's make some variables here. So I'm going to make an address variable, set this to the value 24. So that's the address of my I2C device. And then we'll make a temperature register variable. We'll set this to 5. That's the address of the temperature register. And then there's also a resolution register that's the value of 8. And we'll come back to this because this is one that I can write to. And so I'll show you how to write to one of these registers also in a second. Okay, so now that I have these, let's grab the value of the temperature register. So you just need to call I2C.readFrom_mem. And then you pass in the address of the device. the register that you want to read from, so number 5, the temperature register, and then the number of bytes that you want to read, so 2 bytes in this case. And when I do that, I get back this value here. So this is basically giving me back a byte string, and this /x format, this is basically just saying that this is a hex value, so it's not a printable character. And then this is a printable character, but it's escaped because it's a slash. It's a little confusing. But you can see I can call this thing, and if I hold my finger over this and heat it up, we'll see the value should change. So yeah, like these lower bits changed, like they probably increased. And that's good because I know from the data sheet that lower bit, or byte rather, this lower byte is the temperature data, so that should be increasing if it's going up, and it looked like at least a change there. So that's cool. That's one way to read the data, and I could save this and say, okay, data equals I2C dot read from underscore mem address temp register, and then 2 bytes from that. Read ROM. No, that's not what I want. I want read from memory, and so now the data value has that inside of there too. Another way that you can do this, and I showed this before in the SPY video, you can save the data into a buffer that you allocate ahead of time, because when you call this function, it's actually creating a bit of memory that's 2 bytes long and using that to return the value to you. And that's fine in some cases, but if you're doing this in a loop on a device with limited memory, like remember this ESP only has like I think 96 kilobytes of memory, and some of that's taken up by MicroPython. So if you're constantly allocating little 2 byte chunks of memory in a loop, that's going to add up. And there is a garbage collector, like it will kick in at some point and maybe find unused memory and reclaim it. But that takes time. That's going to be a performance hit. And you can fragment memory to the point where maybe you can't allocate any memory anymore. So it's the kind of thing where if you're used to like desktop Python programming where memory is effectively unlimited, every machine these days has at least probably 4 gigabytes of memory or more. And that's, to an embedded programmer, that's unlimited memory. So you're not really used to having to worry about that. Whereas you come to an embedded board like this, you do have to kind of think about, even though Python is garbage collected and dynamic and really amazing for what it is, you still can't really break the laws of physics or the laws of limited memory on here. So, you really have to be aware of that. Anyways, though, so here's how this works. You create a byte array first. And the size of the byte array is basically how much data you want to read from the device. So I want to read 2 bytes. So I create a byte array like this. And if I look at this, you can see it has just 2 bytes and they're set to the value 0. And then I want to call the function I2C.readFrom underscore mem underscore into. And then I pass it the address and the register, so the temperature register again. And then I pass it the buffer that I created. And I don't need to pass it the size because the Python buffer, the byte array knows how big it is. So it's just going to fill that buffer with data. And so I call that, and now you can see this thing has some value, and it looks kind of similar to the other values that I had there. So again, just a different way to use to read data. This is smart if you're doing something in a loop. You can allocate this buffer once ahead of time, and then every time you call this function, no memory is allocated. Like it's using this buffer that you passed in, and it's just filling that with memory or with the value that it read. So really handy thing to remember. In a lot of cases, you probably want to use this format, but if you're just playing around, it doesn't hurt to try out these functions here. If it's just like a one-off thing, don't worry about it. You'll probably be okay for that. So, okay, so I've got this, and then real fast, I'll just show you how to interpret the value for this. I don't want to run too much longer on this stream. But again, the beautiful thing, because this is Python, I can just write some really simple Python code right here, like a function that converts this temperature into degrees Celsius. Because remember, I have to pull out that fixed point, or not fixed point, but that signed value, 2's complement value from the register. And I pulled this code from Python code that I wrote to use this sensor with the Raspberry Pi. And I can't remember if I wrote this code. I might have ported it from the previous Raspberry Pi code that we had. But anyways, this is the code right here. Like you're literally just grabbing those lower bits of data and then converting from 2's complements to just a floating point value effectively. So let's just throw this function in our code here real fast. And again, this is the beautiful thing I love about MicroPython. So let's see, I'll try to make both these visible. I can just define a function to do this, and then I can use that function forever in my REPL window here to easily do this conversion. So I'm just going to I'm going to make a function. You're going to pass in this byte array of data, and then the first thing it has to do is convert this into an integer value, because the byte array is like an array of bytes, but I want to be able to reason about this as a 16-bit value. So I'm just going to take the first byte and shift it over 8 bits. So it's the upper 8 bits of a 16-bit value. And I'll put parentheses in here just to be a little more explicit about the order of operations. And then I'll OR in the next byte so that this is the lower 8 bits of data. So basically the first byte is the upper 8 bits, the second byte is the lower 8 bits. Really common way to do this is using the Boolean OR or the bitwise OR operator here. Okay, and then now I'll grab the temperature as the lower 12 bits of data here. So if I AND my value with OXFFF, that's basically going to grab those 12 bits of data, and then the sign bit is that 13th bit that we'll look at in a second. And if I divide that by 16, then that's going to do some of this conversion into the floating point kind of value. And now I want to check if that sign bit was set. And so I'm going to look and see, is that 13th bit set, by just checking the AND of that bit. So we grab that bit right there. And if that's true, if that's a non-zero value, then we need to negate this by 256 so that we get kind of the proper negative value for this. And then we just want to return the temperature here. So that's cool. A neat little tip I learned about MicroPython: if you press enter 3 times, it will end the indentation that you're in. So we'll do 1, 2, 3. Well, I guess, yeah, there we go, 3. So it ended that. So a little tip I just learned recently for that. Okay, now if I call this function and I pass in that buffer of data, 21.9375. So that looks like a degree Celsius temperature. And if I hold my finger on here and let's grab another reading. Actually, I'm going to have to type this out again. Let's do I2C dot read from mem into, and then the address and the temperature register and the data buffer. All right, so I'll hold my finger on there, warm that sensor up a little bit. So we grab the value, and then if I read this again, 25.875. So a little bit warmer temperature for that. So it looks like that's working. So that's pretty straightforward and pretty easy. You're just using this read from function or read from mem into, and you're getting the data here. And again, I should note the Pi board has different function names for this, and the microbit has like totally different functions. So go look at the documentation for those. But the basic idea is similar, that you have a device with registers and you're reading from those registers. There's also a write to, where you can write data to a register. I guess I'm kind of running short on time, so I'm not going to go into this in the video here, but I explain it in the guide. And there's a register on this device, the resolution register. And so if I go down to the data sheet here, it explains a little bit more about this. Let's see, yeah, here we go, the resolution register. This changes how accurate the sensor is. So by default, it's in this mode where it will give you temperature in increments of 0.0625 degrees Celsius, but you can see it takes 250 milliseconds to get a temperature measurement. So you can put it into a faster mode where you're only going to get half a degree Celsius of resolution, but it'll only take 30 milliseconds. So you'll get faster temperature updates with less precision, or less accuracy rather. So it's a trade-off, nothing's for free here. But the cool thing is you just have to write these 2 bits here in this register, and you can change the behavior of this device really easily. So check out the guide. I explain you just have to call write to mem, and it's that easy. You pass the address, the register, and then a byte string that has the value that you want to write to this device. So that's how you read and write to the device. I mean, with those basic operations, you can probably talk to almost every I2C sensor, because most of them use that kind of register format. Now, I do mention there are device operations, and this is for devices that don't have that register or memory interface. So for those devices, you only need to know the address of the device, and then you can just send and receive strings of data with them. A little less common. I can't think of a device offhand that uses this approach, but there are some out there. So just something to be aware of. And there are functions for that. So that's read from into, and write to. So there's just no underscore mem for these functions. Exactly the same as the underscore mem versions. You just don't pass in the address of that register, but you still pass in the address of the device. And on the Pi board, it's there's like a recv and a send function that they have. So check out the documentation for that. So that's the device operations. And then for the ESP8266 port, they do have these raw or primitive operations. I'm not going to get into these, but at a very low level, and I talk about this more in the video that I mentioned, I2C is made up of, there's like a start bit, there's a read operation, a write operation, a stop bit, and you put all those together into like a transaction, and there's an acknowledgement of each thing that happens. So you can actually get really low-level control with the ESP8266 port. I don't think you can do this with the other boards though, at least it doesn't look like it's implemented there, and for most hardware I2C interfaces, you don't usually get very low-level control because the hardware is doing that for you. So just something to be aware of there. It is possible to mess with the bus at a low level if you need to for this, so check that out. And then like I said, the I2C slave mode, I don't really get into it in the guide here. The Pi board does support it, so check it out if that's something you want to do, like create a peripheral. But check out the documentation for that because it'll show a little bit more details about how to do it. It's a little less common, but it's a cool thing that you could do with that board. So that's it. I think I'm going to wrap this up then. This was the end of the stream. Oh, I just realized I had this off half the screen for a while, so I think everyone kind of got the gist of it though. So let's see, I don't see anyone in the chat, so I think we'll skip the questions for now and just kind of end this stream. So we'll go back to the main shot here. So thanks a lot for watching. Check out youtube.com/Adafruit. You can see this video and all kinds of other fun videos. Check out twitch.tv/Adafruit. That's where I'd like to do these live streams. I like to do a couple live streams a week, usually one on Monday. This week I couldn't do it on Monday. I was just coming back from a busy weekend in Portland, Oregon. So I had the Portland Mini Maker Faire, Rose City Comic-Con, like Portland Comic-Con, and then the XOXO Festival. So all of them were amazing events. Check out the blog. I put up some photos of the Mini Maker Faire and the Rose City Comic-Con, and hopefully later I'll do a post about like impressions of the XOXO Festival. Everything was really awesome. I loved the Rose City Comic-Con. The cosplayers there were just out of this world. The amount of work and effort and just the quality of what people do is really, really impressive. So, okay, so that's it. I'll wrap this up. This was I2C devices with MicroPython. So, Tony from Adafruit, and until next time, I'll see you guys later. So, thanks.